In the 12 years of National Socialist rule, and especially during the events of the Second World War, Germany became a military giant whose machinery seemed unstoppable. With unprecedented speed and power, the Third Reich forged a path of conquest and territorial expansion across the European continent. Adolf Hitler spurred aeronautical advances that transformed the technology of his era. In just one decade, Germany developed innovations such as radar-invisible planes, spacecraft, and the first jet aircraft, leaping ahead by 40 years. The powerful Waffen-SS stood out for their use of advanced weaponry, including the MG-42 machine gun, renowned for its impressive rate of fire and reliability in combat, and submachine guns like the MP-40, compact and highly effective in close-quarters engagements. Join us to explore the German technology that, under Adolf Hitler's command, came to dominate Europe. Messerschmitt Me 262, the plane that changed the rules of war. The Messerschmitt Me 262 was the world's first jet fighter, whose development began in 1938 under the supervision of Wilhelm Messerschmitt, after the Reich Air Ministry ordered the creation of a jet-powered aircraft. Although jet planes had been tested before the outbreak of the Second World War, it was not until the final months of the conflict that this particular aircraft entered service, marking the beginning of a new era in military aviation. Its design underwent several revisions before reaching its final form. In the initial plans, the engines were to be placed at the center of the wings, with the landing gear under the cockpit. However, this configuration was modified, and the wings were swept back, giving the plane a distinctive, arrow-like shape. By mid-1940, the plans were approved, and the first prototypes began production. 3 aircraft were built to test the design, but the engines were still under development. The first prototype flew on the 18th of April the following year, powered by a conventional Junkers Jumo 210G engine, as the jet engines were not yet ready. The flight was successful, but it was not until November of 1942 that the first test with the final turbojets, capable of 450 kilograms of thrust, was conducted, though the Jumo engine remained on board. The aircraft was designed for multiple roles during combat: fighter, interceptor, attack bomber, reconnaissance aircraft, and night fighter. Its speed was one of its most remarkable features, exceeding 500 kilometers per hour, making it significantly faster than many Allied fighters, such as the North American P-51 Mustang. Despite its speed, it was vulnerable during takeoff and landing due to its low maneuverability in these phases. Therefore, the airfields from which it operated were protected by other fighters, such as the Focke-Wulf 190 D9. Mass production began in July of 1944, and between 1,400 and 1,500 units were manufactured, although only around 300 entered operational service during the conflict. Despite its brief use, the Me 262 managed to shoot down over 500 Allied planes. Its technical superiority over Allied fighters was undeniable, but logistical issues and constant manufacturing challenges, due to Allied bombings of factories and resource shortages, prevented it from having a decisive impact on the conflict's outcome in favor of the Axis powers. A lasting legacy. The Me 262 left a lasting legacy. Its revolutionary design transformed military aviation and served as a foundation for the advancement of jet aircraft in the following years. Aircraft such as the North American F-86 Sabre and the Boeing B-47 were influenced by the German fighter's design. Beyond this remarkable aircraft, Nazi Germany developed approximately 100 innovative and legendary aircraft models during the Second World War. The Horten Ho 229, for example, was a fascinating aircraft. Designed as a flying wing, it featured a revolutionary shape and incorporated 2 propulsion systems. The Horten brothers, Reimar and Walter, equipped it with an aerodynamic structure that enabled rapid and powerful attacks on the enemy. Its plywood construction made it lightweight yet stable, granting it a notable payload capacity. Another striking design was the Bachem-Bar 349, capable of vertical takeoff. After completing its attack, the pilot could be evacuated using a parachute system. However, only a few prototypes were built as it was developed during the final days of the National Socialist regime. Shock troops. the innovation and legacy of tanks in modern warfare. The evolution of tanks began during the First World War, a conflict that saw the creation of the first armored vehicle models as a response to the challenges of advancing through terrain riddled with barbed wire and machine gun fortifications. The British were pioneers in promoting these vehicles, with officers Ernest Swinton and Maurice Hankey playing key roles in conceptualizing the first prototypes. The first British combat tank, the Little Willie, was unsuitable for the battlefield but served as the basis for the Big Willie. The latter became the fundamental prototype for the development of the Mark I, the first operational combat tank. During the 1920s and 30s, tanks continued to evolve, particularly in France and Germany. A pivotal model was the French Renault FT-17, which revolutionized tank design by introducing a fully rotating turret-mounted gun, a feature that remains a hallmark of many modern tanks. With the outbreak of the Second World War, the evolution of tanks reached new heights, especially in Nazi Germany, which experimented with increasingly advanced models to meet the conflict's demands. Under the leadership of General Heinz Guderian, the Wehrmacht refined the use of tanks as an independent force capable of rapid advances and penetrating enemy lines. This approach revolutionized modern warfare and was emulated by other nations, which began to recognize the importance of tanks in mobile battles. German tank models and their evolution. The Panzer III and Panzer IV were the most common models at the beginning of the conflict, though they could not rival the Soviet T-34, a tank that stood out for its sloped armor, mobility, and powerful armament. Confronted with the threat posed by this formidable opponent, the Germans were compelled to create a model capable of countering it. In 1943, after analyzing the characteristics of this powerful adversary, Germany launched the production of the Panzerkampfwagen 5, known as the Panther. This medium tank excelled with its balance of mobility, armor, and firepower, making it one of the most formidable tanks of the era. The Panther's maneuverability, combined with its 7.5-centimeter gun, made it a fearsome presence on the battlefield and is widely regarded as one of the best tanks of the conflict. However, German advancements did not stop there. Concurrently, the Panzerkampfwagen 6, known as the Tiger, was being developed. This heavy tank, which entered service in 1942, became renowned for its powerful armor and 8.8-centimeter gun, capable of destroying almost any other armored vehicle of its time. Despite its strengths, its weight and manufacturing complexity rendered it less practical than lighter models. By the end of 1944, Nazi Germany had introduced an improved version of the Tiger, the Königstiger or Tiger II, which further increased its armor and firepower. However, it suffered from the same logistical and mobility issues as its predecessors. Impact and limitations. Although this heavy tank was formidable in combat, it failed to significantly alter the course of the war due to production and deployment limitations. Beneath the waves, the legend of U-47 and its wolfpack tactics. One of the most iconic German submarines was U-47, a Type 7B vessel. It was commissioned on the 17th of December 1938, and its operational life was relatively short. During its 10 missions, it sank 30 ships, totaling 164,952 gross registered tons, and damaged 8 more, adding 62,751 gross registered tons. This submarine represented a significant advancement in submarine technology of the era. Measuring approximately 67 meters in length and 6 meters in width, it offered excellent maneuverability and the ability to perform rapid underwater maneuvers. It was designed to carry a crew of between 44 and 48 men and was equipped with 6 torpedo tubes. Submarines of this class could dive to depths of up to 230 meters and operate up to 250 nautical miles underwater before needing to surface to recharge their batteries. These submarines were renowned for their speed and ability to quickly evade detection, strategic impact, and the Scapa flow operation. The strategic impact of U-47 was particularly evident during one of its earliest and most notable missions, the attack on the British naval base at Scapa Flow in October of 1939. This daring operation was led by Lieutenant Günther Prien aboard the submarine. On the night of the 13th to the 14th of that month, Brienne successfully infiltrated the heavily fortified British naval base, considered nearly impenetrable, by taking advantage of the darkness and favorable currents. After careful maneuvering, the submarine positioned itself to attack the battleship HMS Royal Oak, which was anchored in the bay. At 1:30 in the early morning, Brienne launched torpedoes that struck the Royal Oak, causing a devastating explosion that sank the ship and resulted in the loss of 833 of its 1,400 crew members. This success bolstered confidence in the capability of German submarines to operate in heavily defended British waters, solidifying the submarine warfare strategy championed by Admiral Karl Dönitz. Wolfpack tactics. The Rudel tactic, or wolfpack tactic, was central to the operations of U-47. In this approach, multiple submarines coordinated attacks on enemy convoys, significantly increasing the chances of success while complicating the Allied defense efforts. This tactic's effectiveness was demonstrated across numerous missions, where U-47 and other German submarines inflicted severe damage on Allied supply lines, significantly contributing to Britain's supply challenges. U-47 became a symbol of the German Navy, especially after its victory at Scapa Flow. Following this success, the submarine adopted the emblem of a snorting bull, which later became the insignia of the 7th U-boat flotilla. The mysterious disappearance of U-47. However, not all missions ended successfully. U-47 disappeared under mysterious circumstances in March of 1941. The exact cause of its sinking remains unclear, with theories suggesting it may have fallen victim to an Allied attack or suffered a technical failure that caused its demise. Other notable vessels. The Tirpitz and U-505. Another remarkable vessel was the Tirpitz, the largest battleship of the Kriegsmarine and the sister ship to the Bismarck. The Tirpitz entered service in 1941 and posed a constant threat to Allied convoys in the North Atlantic. Its impressive 38-centimeter guns allowed it to strike targets at long distances, making it a formidable adversary. However, despite its strength, the Tirpitz never secured a decisive victory and was ultimately sunk by Allied airstrikes 3 years after it began operations. Germany also deployed U-505, a Type 9 class submarine known for its long range. Capable of traveling over 27,000 kilometers, it gained fame for its effectiveness in sinking Allied merchant ships during the Battle of the Atlantic. On the 4th of June 1944, U-505 was captured by the United States Navy during a daring and covert operation. At the time, it was on its final patrol in the Atlantic, after having sunk several Allied ships throughout its career. During one mission, it was detected by Task Group 22.3, which had been tracking its movements. The submarine suffered severe damage from depth charges launched by U.S. ships, forcing the crew to prepare to abandon it. Before doing so, they opened the valves to scuttle the submarine and prevent it from falling into enemy hands. However, in a desperate twist, U.S. forces managed to board and secure the submarine before it completely sank. Significance of the capture of U-505. The capture of U-505 was significant, as it marked the first enemy submarine captured since the War of 1812. On board, valuable documents and an Enigma machine were discovered, providing crucial intelligence that aided the Allied war effort. Wernher von Braun and the V2, the duality of science in times of war. The story of the V2, one of the earliest and most advanced missile weapons perfected during the Second World War, dates back to the late 1930s. Research and development of this technology took place at the Heeresversuchsanstalt Peenemünde, located on the island of Eustom in the Baltic Sea. Wernher von Braun, a prominent engineer and rocket scientist, led the project, which was initially known as the A4. This initiative pioneered the use of liquid fuel, granting greater efficiency and range compared to solid fuel rockets. The first successful flight of the A4 occurred on the 3rd of October 1942, reaching an altitude of 84 kilometers, placing it at the edge of space. This achievement marked a milestone in rocket technology and laid the groundwork for the subsequent development of the V2. Production and wartime deployment. Following an air raid on Peenemünde in August of 1943, production of the devices was moved to less vulnerable areas. This relocation led to the establishment of the Mittelbau-Dora concentration camp, where forced labor was used to manufacture the rockets. A year later, the A-4 was renamed Vergeltungswaffe II, or V2, as part of the Nazi regime's propaganda effort to present the weapon as a decisive factor in the conflict. It was promoted as a response to Allied bombings, with expectations that it would turn the tide of the war in Germany's favor. Wernher von Braun, though deeply involved in the military goals of the Third Reich, also dreamed of future space missions, adding an intriguing dimension to the development of this device. Technical features of the V2. From a technical standpoint, the V2 was among the first large-scale liquid-fueled rockets. Measuring 14 meters in length with a diameter of 1 meter and 65 centimeters, it weighed between 12,700 and 12,900 kilograms when fully loaded. Its payload capacity was 750 kilograms, and it had an approximate range of 300 kilometers. The V2 could reach an altitude of up to 80 kilometers and had a flight time of roughly 320 seconds. The propulsion system of the V2 consisted of a liquid-fueled rocket engine powered by a mixture of alcohol and liquid oxygen. This engine generated approximately 270 kilonewtons of thrust, equivalent to about 650,000 horsepower. The V2 could achieve speeds of up to 5,500 kilometers per hour, making it nearly impossible to intercept during its trajectory. Designed as the world's first ballistic missile, its trajectory could not be altered once launched. The rocket followed a parabolic path, enabling it to strike targets at long distances with high precision. Operational use. The first V2 operations began in September of 1944, targeting London. These attacks were part of a strategic offensive aimed at demoralizing the British population and easing pressure on German forces. The V2 represented a significant shift in warfare, as it was practically undetectable by contemporary defense systems. Its destructive power was devastating, resulting in thousands of civilian deaths and significant infrastructure damage. However, despite its impact, it failed to decisively alter the course of the war. By late March of the final year of the Third Reich, just before hostilities in Europe ended, more than 3,000 V2 rockets had been launched, with London and the port of Antwerp as primary targets. It is estimated that between 8,000 and 12,000 people died in London due to these attacks, and the destruction of infrastructure was extensive, with thousands of buildings damaged or destroyed. A lasting legacy. The V2 is likely one of the most iconic examples of the technological advancements of its time, leaving a lasting legacy in the history of rocketry. Ciphers and conflict. The Enigma as the Third Reich's secret weapon. The story of the Enigma machine began in 1918 when German engineer Arthur Scherbius patented its design. Initially conceived for commercial applications, Scherbius recognized the potential of encryption technology for securing communications. 5 years later, he founded the Chiffrier Maschinen Aktiengesellschaft, commonly known as CHIMAG, to market his invention. The first model produced encoded text on paper, resembling a typewriter. In 1924, an improved version was introduced that displayed letters through lights, making it more user-friendly and accessible for operators. How the Enigma worked. The Enigma was based on a rotor design that encrypted messages through a complex combination of electrical connections. Each rotor had 26 contacts on both sides, connected by internal wiring. When a letter was pressed on the keyboard, the electric current flowed through the rotors, being redirected by the internal wiring of each rotor before passing to the next. This setup ensured that each letter was replaced with another, creating a simple yet effective cipher. By 1926, the German Navy was the first to adopt the machine, followed by the Luftwaffe and the Army. The Enigma became an indispensable tool for secure military communication. Key improvements. Technological enhancements were quickly implemented to adapt the machine to the military's specific needs. One of the most significant changes was the addition of a plug board, which allowed additional permutations, thereby increasing security. These modifications led to the development of the Enigma I, which was officially adopted by the Reichswehr on the 1st of June 1930. Its military introduction represented not just a technical leap, but a strategic advantage for the German armed forces in the lead-up to the Second World War. Enigma's widespread use. It is estimated that between 100,000 and 200,000 units were produced, making the Enigma a widely used tool for military communication throughout the war. The machine enabled the German forces to transmit orders and secret information incomprehensible to the enemy. This was particularly critical in strategic operations, where securing information about troop movements and attack plans was vital. A particularly significant use of the Enigma was in submarine operations. The German submarine fleet, often operating in coordinated groups called wolfpacks, required a secure communication method to coordinate their maneuvers. The Enigma allowed submarine commanders to transmit orders and information about enemy ship movements quickly and securely. Overconfidence in security German High Command believed that the machine's encryption ensured unbreakable communication security. This overconfidence led them to continue relying on the Enigma, unaware that Allied forces had already begun decoding their messages. This critical oversight proved to be a significant error, as cracking the Enigma codes during the Second World War became a turning point in the Allied effort to disrupt German communications. Breaking the Enigma codes. Before the outbreak of hostilities, Polish mathematicians had made significant breakthroughs in deciphering the Enigma. They shared their findings with the British. After the German invasion of Poland, mathematician Alan Turing joined the government code and cipher school at Bletchley Park, focusing on improving Polish methods. Turing and his team developed the bomb, a machine designed to automate the decoding process. This innovative device could quickly test possible rotor combinations, simplifying the identification of the codes used in German communications. Bletchley Park's role. As the war progressed, efforts at Bletchley Park intensified. By 1943, the bomb machines were decoding up to 84,000 messages per month, providing critical intelligence about German movements. Turing not only contributed to the decryption of Enigma, but also laid the foundations of modern computing, demonstrating how the combination of mathematics and technology could change the course of history. Between light and darkness, German innovations in radar and night vision. The Freya radar, developed before the Second World War, was one of the first systems of its kind employed by the Third Reich. Named after the Norse goddess Freya, its designation reflected its strategic importance. The radar was designed to provide complete 360-degree coverage and operated at frequencies between 120 and 130 MHz, with a pulse power output ranging from 10 to 15 kilowatts per hour. Although its range could extend up to 160 kilometers, the Freya radar's primary advantage lay in its complete mobility, offering critical flexibility to adapt to changing battlefield conditions. Key role in air defense. The Freya radar became a cornerstone of German air defense, enabling early warnings of air raids. This allowed for better coordination and response to enemy attacks, particularly in intercepting Allied aircraft. Through its integration into the Kammhuber line, a complex system of radar stations, night fighters, and anti-aircraft batteries, the radar played a crucial role in improving coordination among various defense units. However, it faced significant challenges in determining the precise altitude of enemy aircraft, making it less effective than the British chain-home system in pinpoint accuracy. Additionally, the radar's effectiveness was reduced during the war's later stages due to countermeasures like Dupel, small aluminum strips deployed by the Allies to jam German radar systems. Improvements and successes. Despite its limitations, the Freya radar proved vital in enhancing German response capabilities. Upgraded versions, such as the FUMG 401 and FUMG 41, were developed to improve both range and accuracy by incorporating multiple antenna arrays, addressing some of the original model's shortcomings. Zielgerät 1229, the Vampire night vision device. Another significant advancement in German military technology was the Zielgerät 1229, known as the Vampire. This active night vision system was designed to integrate with the Sturmgewehr 44, the famous German assault rifle. The Zielgerät 1229 used active illumination technology to generate images in the dark, enabling German soldiers to fight effectively in low visibility conditions. This innovation provided a significant tactical advantage, allowing for surprise attacks and improved defensive capabilities during nighttime operations. Challenges and limitations. However, the Vampir's availability was extremely limited due to the complexity of its manufacturing process and the dwindling resources of the Third Reich during the war's final years. Only a small number of soldiers had access to this equipment, which reduced its overall impact on the conflict. Additionally, the active illumination technology required a specific type of infrared light, which was not suitable for all environmental conditions. Furthermore, operational challenges in various terrains and weather conditions hindered its effectiveness in certain combat scenarios. While this system represented a significant improvement in night combat capabilities, its large-scale deployment was not feasible, limiting its real-world impact. The bigger picture. As the war progressed, Nazi Germany sought to enhance these technologies further. However, resource shortages and the pressures of total war prevented many of these innovations from making a decisive impact. Precision weapons, the innovation and limitations of the Fritz X. The Fritz X was one of the most innovative weapons developed by the Third Reich, marking a milestone in the evolution of precision-guided munitions during the Second World War. Its creation arose in the context of escalating aerial warfare, where Axis powers sought to counter the Allies' growing superiority in this domain. Engineered by German designer Max Kramer under the direction of the Ruhrstahl Company, the Fritz X was intended to provide an effective solution for destroying powerful and heavily armored enemy ships, which posed a significant challenge to conventional weapons of the time. The first mass-produced guided bomb. The Fritz X was the world's first mass-produced guided bomb. This missile-like weapon, launched from an aircraft, was specifically designed to attack armored ships. Weighing 1,570 kilograms and measuring 3.5 meters in length with a wingspan of just over 1.5 meters, the Fritz X was capable of penetrating up to 20 centimeters of steel plating, making it a lethal threat to warships. Equipped with a powerful radio-based remote control system, the bomb utilized amplitude-modulated frequencies of 50 megahertz, allowing it to be guided from the attacking aircraft to its target. However, the bomber needed to fly low and circle above the target to manually guide the device, which limited its effectiveness and required a high degree of skill from the crew. Introduction and first successes. The Fritz X was officially introduced in July of 1943 and saw its first combat use on August 29th of the same year. One of its earliest and most notable successes occurred on September 9th, during a tragic episode involving the Italian battleship Roma, the pride of the Regia Marina. Following Italy's armistice agreement with the Allies, the Roma and other vessels departed the port of La Spezia intending to surrender. While en route to the port of Bona, the ships were spotted by the German Luftwaffe near the Strait of Bonifacio. At 4:35 in the afternoon, a group of Dornier Du 217 bombers released 2 Fritz X bombs onto the battleship. The first bomb struck the side of the Roma, causing severe damage by flooding vital compartments and slowing the ship's speed. The second bomb proved catastrophic, hitting the magazine and triggering a massive explosion that destroyed much of the vessel, killing hundreds of sailors, including Admiral Carlo Bergamini. The Roma broke apart and sank quickly, claiming the lives of over 1,000 crew members. Limitations and challenges. Despite its innovative design, the Fritz X faced significant logistical and tactical challenges. Aircraft scarcity, a shortage of bombers capable of carrying and deploying the bomb restricted its battlefield use. Precision issues, its accuracy was relatively limited, reducing its effectiveness in some combat situations. Operational risks. The attacking aircraft had to fly at low altitudes, exposing it to substantial risk, particularly as Allied anti-aircraft defenses improved. Alternative innovations, the Henschel HEs 293. In addition to the Fritz X, the Germans developed the Henschel HEs 293, another weapon designed to target ships. Unlike the Fritz X, this bomb featured a different control system. Instead of requiring the aircraft to remain over the target, it could be guided via cables. From Allied victory to the Cold War, the capture of Nazi technology and its aftermath. After the conclusion of the Second World War, the world underwent a period of radical transformation. The victorious Allied powers, having defeated the Nazi regime, faced a new challenge: the need to access and exploit the vast scientific and technological knowledge that Germany had developed over many years. This effort was not only crucial for rebuilding their own industrial and military capabilities, but also became a central element of the emerging Cold War between the Western powers and the Soviet-led bloc. Operation Paperclip, harnessing German expertise. One of the most significant programs in this context was Operation Paperclip, carried out over 4 years starting in 1945. This secret United States program brought more than 1,600 German scientists, engineers, and technicians to American soil. Among them were prominent figures like Wernher von Braun, renowned for his work in perfecting the V-2 rocket. Operation Paperclip was directed by the Joint Intelligence Objectives Agency, whose primary goal was to ensure that these experts did not fall into the hands of other Allied powers, particularly the Soviet Union. However, the United States was not alone in seeking to capitalize on German technology. Nations like Britain, France, and the Soviet Union also actively recruited German scientists. Beyond Paperclip, Operation Alsos and nuclear ambitions. This phenomenon of talent acquisition extended beyond Paperclip, with initiatives such as Operation Alsos, part of the Manhattan Project. Its main objective was to investigate and secure advancements in Germany's nuclear program, fearing the potential development of an atomic bomb. Beginning in 1944, the operation was led by physicist Samuel Gaudsmit and Colonel Boris Pasch. As Allied troops advanced across Europe, a small team of scientists and military personnel infiltrated liberated areas to gather information on German nuclear research. Despite some initial setbacks, such as the capture of relatively unknown scientists, the mission yielded critical results in Hechingen, where documents revealed that Germany was far from developing a functional atomic bomb. By April of the following year, Alsos agents captured prominent German physicists, including Otto Hahn and Werner Heisenberg, preventing their knowledge from falling into Soviet hands. The detained scientists were transferred to Farm Hall in England, where they were monitored to extract information about their research. Operation Backfire, testing the V-2 rocket. Another significant initiative was Operation Backfire, a military and scientific mission conducted by the Allies, primarily British personnel, at the end of the Second World War. Its purpose was to evaluate the V-2 rocket created by Germany and understand its technology. The operation took place in 1945, during which several V-2 rockets were launched from the Netherlands into the North Sea. British engineers achieved successful tests, achieving greater accuracy compared to the German launches during the war. These trials uncovered significant innovations in rocket design, including advanced engines and sophisticated guidance systems. The Cold War race for technology. The capture and utilization of Nazi technology had a profound impact on the competition between the United States and the Soviet Union. Both superpowers quickly recognized the strategic value of German advancements during the Second World War. While the United States benefited from captured German artifacts and expertise, the Soviet Union also leveraged these resources to accelerate its own technological development. The competition extended to various fields, particularly space exploration, where both nations sought to demonstrate their scientific superiority. The Soviet Union's launch of Sputnik 1 in 1957 marked a turning point and shocked the Western world. This Soviet success heightened fears in the United States of falling behind in the technological race, an event known as the Sputnik shock. It led to increased investment in research and development, the arms race and space race. The competition to control Nazi-derived technology intensified tensions between the superpowers. Each new advancement by the other side, no matter how minor, was perceived as a threat to national security. This dynamic resulted in an accelerated arms race, encompassing not only military developments but also civilian achievements, such as space exploration. In response, the United States heavily invested in programs like NASA, aiming to maintain its dominance in the space domain,